Ren here from Columbia to talk about photoacoustic imaging of nonlinear physics and also open problems. Thanks a lot, Q, for joining us for our international inverse problems seminar.
Thank you. Thank you very much for the invitation to speak here. As I made it clear to Knut, I don't really have a lot of new results recently, especially for this community where people are looking at more on the technical side. So I decided to talk about a problem where I think that we need a lot of help. There were still many very interesting problems from the practical point of view that need to be solved. Although again, this topic looks a little old by now. So this is about, again, photoacoustics, but it's in a regime where you can try to add a little nonlinear physics in it. So again, I'm going to be mainly just to tell you what the problems that we have and where we need help. So this is a very, might be a very strange talk to a lot of you who are interested in technical details. So again, my main idea is to introduce you to the problems. I'll give you a quick introduction about why people are interested in this, and then tell you what are exactly the problems where we need some theoretical development. There are a lot of computational problems actually here that are even more important for some of the applications that I won't have time to talk about, but I'll try to give you some theoretical problems to think about. So again, this is photoacoustics. So just for those who don't know this business, so this is a method that was developed one step further of the optical tomography, which is again where you send a near-infrared light into tissues and you measure acoustic waves that come out of this tissue. And from that, you want to reconstruct the optical property of the medium. So this is the, this phenomenon is called photoacoustic effect. Basically, when you send photons in this medium, absorb light, absorb those photons. So once they absorb photons, they get heated. When they get heated, they expand because this is elastic medium basically. So this expansion will be become a contraction if you stop the photons. So if you send a quick pause, this after the photons has passed through the medium, this will cool down. So the cooling will introduce contraction, and this expansion contraction process will generate acoustic waves, ultrasound. Again, this is just one simple naive explanation of the process. There are in fact many more methods to generate signals in this case, but this is the most naive situation where you couple the photo propagation process with ultrasound signals. So there's a related modality that everyone probably knows. This is called thermoacoustic tomography, which is based on the same principle, but you, instead of using near-infrared photons, you use microwave. And that turns out to be beneficial in terms of its penetration ability, but on the other hand, there are a lot of issues related. So this is now less studied than the photoacoustic case. All right, so the process, there were two processes involved. One is the propagation of photons inside, and this is very often described by the radiative transport equation. I'll mention this later, but you know, the most accurate model you could think of is, of course, to use Maxwell's equation, but that is too expensive to look at in this setup. So a more macroscopic model, this is a kinetic model, is very often believed to be an accurate model already in the community, at least in the optics community. So you have density of photons that is a function of both its position and its direction of travel. So x is a position, v is travel in direction. So you have basically a free transport term here, and then along the trajectory you could be absorbed. So this is sigma A is the absorption coefficient. And then there's a scattering mechanism S here, K operator here, that tells you how your photons travel in one direction, get scattered into another direction. So this, you also see a sigma here. This was due to the fact that they are, so this sigma S here balanced the sigma S on the other side. One is on the part where you have photons that get scattered into a travel direction, and the other is the part where your photons travel in a direction get scattered in other directions. Okay, so that is very often people combine these two terms, but I leave it like that for the moment. So what is important is here that you have this sigma A, which is the absorption coefficient. Sigma S is a scattering coefficient. And then you have this scattering mechanism. It doesn't matter for the moment or for the rest of the talk, but there's this scattering operator here. Okay. So this solution, this is a phase space equation in the sense, again, that your solution U is a function of both the spatial variable and the velocity variable. This velocity in this case is normalized, it's on the unit sphere, so it's mainly direction. This is a monoenergetic case. All right, so this is simple enough. So this propagation of photons, they get absorbed, and the total absorbed energy is described by the absorption coefficient times the density, local density. So this U is the density of photon at a position X. And that density is just the average of photons traveling in all directions at that specific position. Okay, so this integral here is what makes things very messy, as you will see later, that make this problem very hard to analyze. So again, the data here, or at least on this level, so the absorption is the pressure field generated is proportional to the absorption coefficient, the solution of the transport equation, but average over U times another coefficient. This is a Grunausen coefficient. That is another physical coefficient that people are interested in reconstruction. So after this, after you generate this initial pressure field, then it's get propagated. The linear, and one of the model people use very often is the acoustic wave equation. Of course, we know that you can use more complicated models. But again, I'm not going to touch this part. So this is basically what we have. So what is great about this modality is really that the acoustic process and the optical process are decoupled in its physical property, meaning that the ultrasound speed, here, this C here, has nothing to do with the absorption coefficient and the scattering coefficient. So in the ultrasound regime, very often people think of this sound speed constant, that is tissue almost like water. So this is an independent coefficient. In most cases, it's assumed known, but there are a lot of interest in reconstruct that as well. And there are famous paper like by Stefanov Ullman that shows that the simultaneous recovery of all these coefficients is not a great problem to look at. Okay, I'm trying to simplify everything, but that's basically what it is. All right, so again, what you do is you measure the pressure data on the boundary of your domain. And from that, you want to reconstruct basically the three coefficients I mentioned in this. So the Grunausen coefficient here, the absorption coefficient, and also the scattering coefficient. Okay, I'll show you later that the scattering coefficient is very often for practical application is less important because it changes less when there's a tumor or there's not a tumor. The absorption is really what people are interested in, and also the Grunausen coefficient. Okay, so again, this is for people who don't know this process. The inversion, because your measurement is the solution of the wave equation, right? So the inversion process is very often decoupled into two steps. One is you take the pressure data, you get this initial condition H. Okay, so this is just basically a time reversal type of problem for the acoustic wave equation. This has been studied a lot and different type of scenario. I'm not going to mention any of that. So what I'm interested in is the next step. That is, once you have solved this problem, you try to do reconstruction of the Grunausen coefficient, absorption coefficient, and the scattering coefficient from this data that you get from the acoustic inversion. Okay, so what about nonlinear physics? So the model that we take here, in this case, for instance, the absorption here is a single photon absorption, which means an electron that absorbs a photon and get excited and jump into another state. So this is a single photon absorption. It turns out that people are interested in multi-photon absorption, for instance, two-photon absorption. Because this is a very special type of absorption. So this occurs very rare, but because it's rare, it's related to very specific proteins, for instance, in tissues. So for instance, two-photon absorption is a case where one electron absorbs two photons simultaneously and then get excited to, of course, a state that has a higher, much higher energy than a single photon absorption. Okay. So again, this is type of absorption that occurs very rare, but on the other hand, they are very useful because if you can, for instance, manufacture certain material that absorb this way and you inject it into tissue, then you can see this type of absorption only, right? You can neglect the background because if you are interested only in two-photon absorption, if the background has no two-photon absorption, what you injected has two-photon absorption, then there is a way to easily see what you injected. Of course, this also happens in nature in the sense that there are specific molecules that do this type of absorption. I mean, this is just one example. There are many other examples of this type of absorption or emission that people can use. So this is just to say that such phenomenon, this type of nonlinear phenomenon, are useful in practice. Again, none of us care about that particularly because we don't work on that in experiment, but let me tell you the model. So if you add this two-photon absorption, for instance, so again, two-photon absorption is really the event where you absorb two photons simultaneously. So naively, you can think about it, if you have single photon absorption, the absorption is proportional to the absorption coefficient sigma A, so to the density U, right? Two-photon absorption, the total absorption will be proportional to U squared, because if U, there's a probabilistic representation of U. U is basically the probability you observe this photon at this location traveling in that direction. Okay, if after normalization, you can think of that. So this U times U is basically the probability you see two photons that sit in the same location traveling in the same direction essentially, right? But this absorption is independent of direction. So there's a complication here. That is, this instead of being a U squared, you have a U average squared. So again, U average is just the average of U over all directions. Again, this looks nothing too bad because still in this quadratic term is only related to U, not gradient of U. But this, again, this averaging here actually caused a lot of trouble in the study of the problem, at least for me and the people who work with me. It's hard enough to have that problem. So nothing else changed in this game when you have this nonlinear absorption, except that because of this absorption, so you have the initial pressure that's generated now has two terms. So this is the single photon absorption part, and that is the two photon absorption part. Okay, so this is your internal data now. So this sigma, char here is still the Grunasson coefficient. So you have this quadratic form of absorption. And let me emphasize again where the problem is. The problem for analysis is really that if you look at this data, so the data here, sigma times U plus sigma times U squared, these are both averaged. If you look at what we have in the equation, we have a term that looks like this, right? Sigma times U plus sigma B times U squared. What is the difference? The difference is that the term in the equation has a U that is not the average of U, but in the data, okay, that you have this average because the heat generation process only depend on the average, not the specific traveling directions of the photons. Okay. So this is where the major problem is for the analysis. So the rest is not changed. So the acoustic process is not changed. So you can just neglect that part in this new modality. Again, this is not the only type of nonlinear physics you can add here. This is just one of the examples that show here. All right, so by now there are already quite some problems in terms of applications. First is that, again, this model, if you look at the engineering literature, people use this model, this nonlinear transport model. But where does it come from? How do you get this nonlinear model from, for instance, the Maxwell equation, the model that you would use on a more fundamental level? That is not completely clear. So again, this Maxwell type of model, or the classical ones that people in physics use. So the first question that, from mathematical modeling point of view is why this model makes sense. I don't know. Actually, I think there's a way to justify that so we know that, if you don't have this nonlinear term here, if it's a linear term, there's a way that you can go from the wave equation to the transport equation. Many people in the audience have done something like that. But now, because of the nonlinearity, things are not as straightforward. So, but still, I think I had some simple calculation that says very likely the framework of deriving linear transport will still work in this case. But again, there's not one simple paper on this so far. The second thing is that this looks like a simple nonlinear, semi-linear transport equation. But we don't actually know a lot about the behavior of the solutions, Wilcoxness of the solutions, okay? So I'll mention a little bit later on this issue. But again, before we look at anything, those are actually modeling issues that that need to be addressed from practical point of view. So another thing is that we all know that computationally nobody wants to use transport equation, right? But I still argue later that it actually makes sense in the photoacoustic case to use transport equation. In the classical inverse boundary value problem for optical tomography, actually don't gain a lot because the problem was so yield conditioned. But in this case, actually you gain. So there's a point to use that. But in any case, the naive and the most naive thinking when you look at this model is to say, what is the corresponding diffusion approximation, right? So if you look at this process, this transport equation, it's very easy to see that you can come to the corresponding semi-linear diffusion approximation if you are in the diffusive regime. So as long as your solution for the transport equation here remains bounded, remains small when you take this diffusion approximation process. So the diffusive regime is the regime where you have your scattering is very high. Basically, your mean free path compared to the size of the domain is very small. So again, this is just a naive explanation of how you get this diffusion model. There's not a rigorous justification in this case either. So this will be something that is very nice to see. Intuitively, if your solution, if you know that this transport solution is going to be, you know, on odd one, again, odd one really means compared to the boundary condition, then this should be a straightforward calculation because you will see you can treat the using the same scaling in the classical diffusion approximation. You rescale your absorption and scattering in different norms, a different order. So if this solution U remains odd one, you can see that sigma B times U remains odd one, then the scaling should be the same. But again, this is just a naive thinking here. There's really not a rigorous justification so far. So that would be something nice to do. That's another problem for anyone who is interested in this business. Okay, so what about inverse problems? So I told you the physics here. So let me quickly mention a few things in the on the inverse side. So I'll start with the simple case, diffusion case. Suppose we know really, you know, we are talking about this diffusion equation and everything is valid. This is a nice model here, okay? And we have this data. This is H is the data. So in this case, so here, forget about the absolute value here. I'm just saying that we are looking for non-active solutions because in physics, we only care about that. So, you know, I put an absolute value here, but forget about that. So what is good in this game is, of course, you see that sigma U, sigma B, U square appears in your data in exactly the same manner. So sigma A times U, sigma B times U square. This makes the whole problem much simpler than the transport case. Remember, in the transport case, what happened in the data is different from what happened in the equation. Okay, but in any case, you have this simple problem here. So how do you solve this problem? The first thing you notice by very simple calculation is that if you are really interested in reconstruct, so this I forgot to mention for people who don't know, this gamma here, diffusion coefficient, is related to the scattering coefficient in the transport equation. Okay. So this If you are really interested in reconstructing gamma, sigma A, sigma B, now you have 3 coefficients here, and also the Grunasing coefficient, you cannot do that. This is, of course, expected. You can see it easily by doing a very simple transform. This was the classical Liouville transform. You can do a transform so that you can take out the gamma term. I think everybody here knows this trick, so let me not spend too much time on this. But you do this transform, you have a Schrodinger equation. You take out the gamma, so gamma become part of the potential here, and you see a nice structure here. This is in the linear case. The only thing that is different from the linear case is there's an extra nonlinear term here. So you have this classical potential that you see in the classical way. And then you have an additional term, another one here. This one is new because of the nonlinear term here. So if you do the transform, of course, now you have of the data. In the data, you have also two more combinations of coefficients. Okay, so this is a classical potential. This is a new potential here. This is a new potential here. This is a new potential. So you have 4 parameters basically that matters, because this Schrodinger equation, that solution is determined only by these 2 combinations, right? All right, so it turns out that you can show easily that among these 4 combinations, if you know 3 of them, that's all. You know the whole data. In other words, this data is only decided by 3 of the 4 combinations. So this gives you quickly a very simple, naive justification that there's not a uniqueness in this case if you want to reconstruct all 4 coefficients. Okay. Again, you see this from the classical calculation when you do the classical optical tomography problem. So this was also when you do EIT, when you transfer that EIT problem into the Schrodinger problem with a potential. This classical result of Ullmann, Sylvester Ullmann and Neckman were done in this type of transform. All right, so that very naive explanation says that you cannot recover all 4 coefficients. Okay. What if you want to recover 3 of them? Okay, so this will depend on how much data you have, it turns out. So if you have the whole, Dirichlet to Neumann map, not Neumann map, Dirichlet to the internal data map, then there's a way that you can use this classical idea of linearization, that is linearize the forward model, not the inverse problem. This is, from my reading, the first idea was given by Isakov, but then there were so many results from a lot of you. I'm sorry if I forget your name here. Those are the names when I read papers, I saw those. So I'm pretty sure there are many, many more people that have contributed in this direction. I would love to know more. If you tell me what you have done, I would love to read. But in any case, in this setup, if you have this infinite number of data, what you can do is to do a linearization. So basically you have this linear and nonlinear problem. Again, many of you here know this business. What you do is you send a small data in so that this nonlinear term here, quadratic term here disappear. Or, on the first order, it doesn't matter anymore because the solution is small, so solution square is smaller. Naive explanation here. So you can do this trick here to split the problem into 2 problems. Okay, one is the classical problem. If you do this linearization on the first order, you would kill the semi-linear term, which gives you this classical problem. So if you think about this V as the U, this is the classical diffusion. So this is a diffusion problem without that semi-linear term. And the data is changed into also the classical case where you have sigma chi. I always forget how to pronounce this, chi times sigma A times V, the solution, okay? So this is the classical problem that was first solved by Bao and Woman in the case where you don't include this chi here. If you include the chi, you can show again, just by doing what I just showed you, this transformation, you will transform to say that you cannot recover all three coefficients here, but you can reconstruct any two of them. So in this case here, you really have gamma, sigma A, and the chi here. Okay, there were only three coefficients. Sigma B disappeared. So you can recover any two of them uniquely. There was some stability, you can say, etc., etc. I don't want to get into this. But once you finish this step, the next step will be easy, because after you do the reconstruction of, let's say, the sigma, gamma, and whatever this chi is, after that, you see that your problem becomes much easier, right? Let me come back to this equation. So if you know gamma already, you know sigma A already, you know chi already. So this basically you can, from H, you can get the solution U already, right? So once you know the solution U, you see that you can get sigma B. Or you can just say that I can put sigma B times U, I can construct that and put this here, I can solve this to get U, etc., etc. So you should believe that once you have this step, it's very easy. Again, this is a linearization of the forward of the model itself, okay? Not the linearization of the inverse problem. The problem is still nonlinear. Again, I know that many of you worked on this type of problem, so you know this, how it works. What about if you don't have this luxury of doing this linearization rigorously? Let's say you have only 3 data sets. Okay. Can you try to reconstruct 3 of the 4 coefficients from 3 data sets? Okay. So in that case, it turns out that the problem is still non-trivial. At least, again, I don't know how to solve it. But if you linearize the problem, I don't know how to explain. So this is a linearization of the inverse problem, okay? That is, you really look at perturbation of the coefficient around some background. If you linearize the problem, then you can show that there's a uniqueness if you in the reconstruction of these 3 coefficients, gamma, sigma, A, sigma B. Okay. Again, after you linearize these problems. So this is for the linear problem. For the nonlinear problem, we still don't know how to solve that problem. Again, this will be a great problem for people in the audience. They are good, I think they are good mathematics to do there. So even in the case of, I said at the beginning, you cannot recover all 4 coefficients, right? So, and I say that in 3 coefficient case, actually, we only know how to solve the linearized problem. What if you do 2 coefficients? So it turns out that it might be embarrassing to say, even in the case of 2 coefficients, okay, so that is sigma, again, this chi here, sigma A, sigma B, gamma. If you want to recover 2 of them, okay, this looks now very, very simple, right? Still, we don't know how to solve it. We only know how to solve the case when you choose this specific set of problem that coefficient, that is sigma A and sigma B. This is like cheating here because this is the simplest problem, right? Because if you know chi, you know gamma already. So the data gives you this combination here. And you can put that combination into the diffusion equation to figure out what the solution is, right? You replace this term here by the H because chi you know already. So you can solve that for U. Once you know U, you can solve this for two different U's. Once you know this for two different U's, of course, you can combine them to solve for sigma A, sigma B, right? To form a linear system there. So that is a very straightforward way to do. That's why I know how to solve it. But beside that two combination, actually, if you take these two coefficients or these two coefficients, I'm missing sigma A here, but this sigma A. Okay. We actually don't know any theory here. Okay. So let me say that the reconstruction of sigma A, sigma B are of course of interest, but this chi is also something very important for practical applications. So it would be ideal, even if you don't want to recover the diffusion coefficient, which does not change a lot when there's a tumor or there's not a tumor. Okay, even if you want to say that let's fix that, try to recover the other three, as I said, we don't know how to do it. So again, please help us if you are interested. All right, so these are just numerics, of course, shows that, yeah, you can do the reconstruction. Actually, everything looks beautiful. You don't care, nobody cares. But let me say that these are really results that you actually study from the acoustic data. Try to do a minimization. It's computationally crazy, but okay, it shows that you have indeed, if in terms of reconstruct sigma A and sigma B, you have a very stable inverse problem. And the reason we did this simulation was because in the literature, there are people who did the experiment who claim that they don't know how to split sigma A and sigma B. They only reconstruct this quantity H. So in the reconstruction, they do a backward propagation of their acoustic data, they get this term. And then they want to split sigma A, sigma S, because you don't know U, so you cannot split them. So what we say was basically that, if you have two different data sets, you can do that. All right, so that was in diffusion. In this very naive, simple case, there are so many problems we don't know how to solve. Again, let me emphasize that this is really something that could be useful in the sense that this photoacoustics, the first step is very mature now. And if you look at, people are pushing it to get FDA approval. And there were so many people do preclinical studies, et cetera, et cetera. So there's a chance that what we do here could be maybe remotely useful in the future when you really want to do quantitative imaging here. Okay? So again, even in the diffusion case, it's very useful. So what about in the transport case? Basically, my message is that there's nothing that we know. So let me remind you what is the model. The model is, again, this simple V dot gradient U plus the absorption term, single absorption, and plus second order absorption. Okay, this is the scattering is always there. So the data is sigma times U average, sigma B times U average squared. Okay, U average is this. Okay, so from this data, okay, suppose you now have this H, can you reconstruct sigma A, sigma B, sigma S, and chi? Okay, the first thing that we see is actually we don't have, again, a well-Posness theory for the model to begin with. So we had recently a result where we say that if the boundary data is small enough, so there's a precise characterization here, how small it need to be, but this might not be the optimal one. This was what we can gain by doing some kind of fixed point iteration. But my point is, again, for small data, so in practice, when you look at this second order effect, you really need a very strong source. You really need large source. Otherwise, this sigma bu square term actually don't matter because sigma b is very, very small. So you need this u to compensate this, okay? So this is exactly where, the theory here is very different from what happened in application. I'm not saying that you cannot improve. I'm saying that we don't know how to improve, okay? So if the boundary data is small enough, then you can show that there's a unique non-negative solution to this problem. Again, we are looking for non-negative solution only, okay? So with this result, you can do some linearization, as I mentioned before, but before I talk about that, so the first question that I want to ask is, in the diffusion case, we know that we cannot recover 4 coefficients simultaneously, right? It turns out that we don't have an easy transform like in the diffusion case to show that you cannot recover all 4 coefficients simultaneously. Actually, I talked to Guillaume Ball, and he always thinks that there's a possibility to do that when you have infinite data in the transport region. I don't see how, but this is a problem that is not known yet. So this is in a case where sigma A, sigma B, for people who are familiar with transport equation, you see that my transport equation here are very simple, meaning that the sigma A, sigma S, sigma B, they only depend on the time variable, okay? If you allow them to depend on the velocity variable, then there's a easy unique non-uniqueness you can result you can construct. So we did that earlier in the linearized case. Okay, so that was the first question that we want to ask. The second is, of course, if we know that for small data this forward problem is well posed, then we can do this linearization technique that I mentioned before in the diffusive regime to solve the inverse problem for at least for small illuminations. So this is the same type of game. You show that you can linearize your forward problem. You send in small data so that your quadratic term disappear, and then you perturb from that to get the next order in the same flavor, okay? So if you do that, we recently did this. If you do that, what you see is that again, on the first order, you will go back to the transport problem with a linear transport, so the nonlinear term disappear. Sorry, this K here is different from the K before because this K is K minus identity because I moved the sigma S to the right-hand side, okay? It doesn't really matter there, okay? So you have the classical transport. So again, the nonlinear term disappeared in this game. And the data now also happened in the same way, that is the second order term disappear, okay? So you have only sigma times chi times sigma times u. From this, if you have, again, the full map, then you can, this problem is solved in the case of reconstructing sigma A and sigma S. Okay, not chi. If you assume chi is known, then the result of our Julier and Jognan shows that you can uniquely recover sigma A and sigma S. In fact, a little bit more in the kernel of the scattering function. Okay, so still, if you put chi here, we don't know what to do here. Okay, there's not a result that tell you that you can recover chi sigma A and sigma S. Although, as I said, Young believe that this is the case. I don't see how you do it. Some linearization tells you probably not. It's a completely open problem. So once you have done that, so once you have reconstruct sigma A, sigma S, and chi, let's say you can do that. The next one is to recover sigma B, and that is an easy problem because there's only one coefficient there. So there's a stability that you can get. Again, I'm not going to talk about all the conditions you need, et cetera, et cetera. So I'm running out of time. So let me quickly say a few words on the case where you cannot do this linearization, but you have a finite number of data. Can you reconstruct all three, let's say any three coefficients with three data sets? It turns out that you can reconstruct two of the coefficients, sigma A, sigma B, two of the absorption coefficients with two data sets. And the very restricted conditions, I'm not even going to bother to show you what are those conditions. So we had a preprint on archive on this that you can read. It's a very messy calculation, but it shows that if you are willing to be doing things under those conditions, there's a way you can recover sigma A and sigma B. So sigma A and sigma B are the two absorption coefficients. Yes, in the transport equation. Okay, so this was just to show that in fact, this result tells you that if the scattering kernel is isotropic, if this K has an isotropic kernel identity, then there's a fixed point iteration you can use to reconstruct the coefficient. Not only that you can do that, there's a unique result, but there's an explicit procedure that you can do that. Because I'm running out of time, so let me skip this. All right, so I show you that basically what we know, essentially nothing, right? There were four coefficients. We don't know the four coefficient case. We don't know the three coefficient case. We know a two coefficient case and the very restrictive conditions. So here are what I want you to look at if you're interested. The first was what I just mentioned. Is it possible to recover sigma A, the two absorption coefficient, together with the chi? The reason is that this chi, again, if you talk to people in engineering, they always say this is very important. Sigma S, you can forget about it if you don't care, but chi is very important. So this is not even know, if you have infinite number of data sets. Can we do that in finite data set? And this is even more embarrassing that, even in the linear case, if you don't have the nonlinear effect in the linear case, we don't know if you can recover chi and sigma A. We know it if sigma S is 0. Okay, that in that case, the transport equation become a linear ODE in the traveling direction. So you can do everything you want, but beside that, we don't. All right, I mentioned this. I mentioned that you don't care about sigma S. There's a reason that you can forget about sigma S for practical reason, but also there's a stability estimate that tells you that sigma S has an impact on the other coefficient in the reconstruction process in a very controlled way. That is, if you have some uncertainty in sigma S, you can show that its impact on the reconstruction of sigma A and sigma B is minimum. So this constant is very small. Actually, they are numeric simulations tells you that. Again, I don't know how to make it explicit, but there are numeric simulations in the diffusion regimes to tell you something like this. All right, so I think I'm done, but let me just say that I just give you one concrete example. There are many, many cases in application that people care. For instance, when they introduce fluorescence, that is, instead of having transport on one wavelength, you can have light on two different wavelengths for applications where you want to inject stuff into tissues. Okay, so you can have nonlinear emission, nonlinear absorption plus nonlinear emission, etc., etc. So let me stop here. So this was just to say that in that case, there was some silly result you can construct, but I really want to come to stop here at this place. Where is it? Oh, not here. That is my whole point here. That is to say, there are a lot of very important problem, important in terms of application. Okay, I don't know, it is mathematical enough for you, but it looks very interesting to me. There are a lot of problems here that need to be solved. The transport equation, there were a lot of people, not really a lot, but many people have worked on that. Gunther and Clement had some nice work in the early years for the setup of optical tomography. But since then, there was not a lot of recent results on that. So again, I think from practical point of view, this is a very nice area to get into. So if you are interested, I'll be happy to talk to you. Sorry to be over time. Thank you very much.
Thanks a lot, Keith, for a great talk. So, so the floor is open for questions. So if you have a question, please unmute yourself. We have time for some questions.
Excuse me, can I ask a question, please?
Yeah.
Yes. I didn't understand, how do you proceed to the linearization when you have finite number of data? You talk about some linearization.
When you have finite number of data, you cannot do linearization exactly, right?
Okay, so what is your meaning of linearized problem?
You can still do a approximation, finite difference approximation, right? But you can really not do that in a rigorous, in the sense that you are going to, the uniqueness result you are going to have is the uniqueness for the true problem. You can indeed do this as approximation. I mean, in practice, you can always send a small source and then change it a little bit, and then use the differential data. I think that would be something for practical purpose. That would be something to do. But again, one of the things that bugs myself a lot is really that all this linearization thing was done in a case where you have small data. So this is at least this two-photon absorption or two-photon emission process. This really requires huge source, very strong source. If you look at the literature, you can only measure, the signal is only strong enough to be measured when you have very strong boundary source. So for practical purpose, it would be interesting to look at ways to go beyond this linearization approach. Again, many people have done a lot in this linearization, and I'm not trying to discredit anything. I'm just saying that for practical purpose here, there's an interest to go beyond that. Okay.
Thank you.
Okay, I have a question, Plamen Stefanov.
Yes.
Okay. Okay, so the question is about the relevance of this model. So this kind of quadratic nonlinearity, understand?
Yes.
So how common is that? I mean, you show something on the last slide, and what does it really mean in terms of its physical meaning? So is that the right nonlinearity, in other words? First, it has to be positive, right? I mean,
yes. So we are looking, I didn't talk about this. Everything has to be positive, even for the diffusion case. When you shoot solutions, you're looking for positive solutions. So this, in the engineering community, people really care about, this type of nonlinearity for not just 2-photon absorption, 3-photon absorption, 4-photon absorption. This is, the chain of reactions that are getting rare, more and more rare. The problem is that, at least in the photoacoustic case, the only type of nonlinearity people can generate sufficient signals to be measured is the second order one. The third order one is you cannot see it. But the third order one, people do boundary measurement. They do a lot that, like this recover of this 3-photon absorption. For instance, if you just Google 3-photon, 2-photon absorption in the optical literature, there are a lot of people doing this. They have ways to reject some background photons and only measure those second order, third order effect. In the case of photoacoustic, you cannot do that because the heat that's generated is really came from this background plus the second order. So if you don't have enough second order effect, your measurement will be polluted. If it's polluted by noise, you cannot see the second order effect there. So this is what makes it very hard to measure this in practice. Even now, there are groups that publish results say that you can measure this. There are other groups say that you have to be very careful, how accurate you can measure your data to make this work. So I'm not an expert on that, but I know that once you go to the next order, it's even much higher to see it in the boundary value case. That is, when you do this scattering measurement, you focus on specific points where you essentially have lengths that kick out the rest of the photons and only focus on these rare events. In those cases, if you measure 3 photons, 5 photons, it's probably enough. But here, no, you really need a huge amount of photons to generate the heat. So I don't know, at the end of the day, how can you go out of this physics to even more high order ones. But yeah.
My question is mostly what is even the meaning of what we have here. So we have U squared multiplied by something. What is the significance of that? I mean, is that 1 photon, 2 photon absorption? What does it even mean?
Which one? The sigma b U square?
Yeah, what is the meaning of this term?
But you can think of these, there are two explanations. One is you can think of this sigma A plus sigma B times U as the total absorption, so that you have this absorption that depend on its the intensity of light. That's one way to explain this phenomenon. Actually, people say this is different. I really don't know that. You have cases where the absorption depend on the density. So basically sigma A can be written as sigma A plus sigma B times U.
Yeah, I see your point, okay.
Yeah, so that is one explanation. If you want to look at this nonlinear effect, that is a more popular explanation in the literature.
Okay.
So another questions for QE? So I was wondering, you mentioned that the chi is important from the practical viewpoint. In some sense, it's possible to say physically what it represents, sort of in the inverse problems, is associated with a tumor, or what does it represent?
Yes, so this chi on a very superficial level is related somehow to the sound speed, for instance. So this is why a lot of them think that it's very important. It's really the physical, one type of physical property. There's actually related to several quantities, but I mentioned related to the sound speed because you see the sound speed in the game, right? So the sound speed is here. I say that the sigma A, the absorption coefficient optical property has nothing to do with C. It looks like chi. I mean, this is still something that is debatable in the literature actually, because some people say that this chi depend on C in quadratic form or whatever. Other people say no. But you know, it's something that the engineering can relate to for instance, specific heat of the medium, speed of sound in the medium. I forgot what are the other parameters related. So that is something that at least I was told that chi is very important. Sigma S is less important for the reason I mentioned before. So if you look at tissue, sigma S really changes not as dramatic as sigma A. When there's a tumor, there's not a tumor, or when there's more oxygen in the blood, or there's less blood, less oxygen, sigma A really changes a lot. Sigma S does not. So many times people can just use a background sigma S. You know, you do some unhealthy tissues and you put that into the model, and then you look for other parameters. And what I show you later was that you can actually see a kind of justification of that, in the sense that you really, if you look at the impact, if you put a wrong sigma S, you look at the impact on the reconstruction of sigma A, sigma B, that impact is small. This constant C is small. I mean, we don't have any analytical thing that explains that, but numerically you can see that, especially if you, instead of changing sigma S, you change, for instance, sound speed, then you get something dramatic. Even smooth sound speed get dramatic. So there's a reason, maybe there's a good reason to, if you cannot recover all four, there's a good reason to kill sigma S instead of the other parameters.
Yeah. Well, there are no other questions. Let's thank Q once again for a very nice talk. Many interesting problems and interesting challenges. Thanks, Q.
Thank you very much.